Before I look at maximum power theorem, it is important for us to note henceforth, unless otherwise stated, we will always assume there's an internal resistance in any EMF source that's given. And in this case, with an internal resistance, it will also give rise to power loss. Let's take a look at the example. So in these questions, we have an electrical source with an EMF of E and internal resistance R. And the external resistance is capital letter R. So with that, the power dissipated by actually the cell is equal to the power dissipated across the load and the power loss in the internal resistance. So from this, we can derive the expression to here. So from here, we can derive that E is equal to the potential difference across the external resistance plus the potential difference across the internal resistance, which is IR. So let's take a look at how we can maximize the power output at the load while minimizing the power loss. So one way to do that is to look at the output efficiency. So we're taking the power of the load divided by the power input provided by the cell. So in this case, we use I squared R divided by IE. So we'll arrive at an expression, and from here, we can arrive at this expression. So from here, we can sketch a graph of efficiency versus R. And that's the shape of the graph. And from the conclusion of the graph, it indicates that if you want to maximize the efficiency, then in this case, we want R to goes to infinite. If R goes to infinite, then efficiency goes to 100%. Let's take a look at an alternative way to maximize the power. The alternative way to do that is to derive the power dissipated at the load in terms of capital letter R and small r. So in the same way that we did for the earlier one, we start with IBR, and then we have I squared R, and we place the current as E divided by R plus R. And from there, we end up with this expression. If we were to sketch a graph for this, we will end up, the graph actually has a maximum point, and you will end up in this manner. So from the graph, we know that if you want to extract maximum power, that occurs when the external resistance is equal to the internal resistance. So there are now two approaches to maximizing the power load. So which one should we follow? Should we follow this graph here and make R and make the external resistance equal to the internal resistance? Or should we maximize the external resistance so the efficiency is 100%? The answer is that this is not the correct approach. The reason is because when R goes to infinite, if R were to go to infinite, this graph will indicate that the power at the load that to be extracted will go to 0. Hence, the correct way to maximize power is to have the external resistance equal to the internal resistance. That is what the maximum power theorem states. And it says that maximum power is delivered to the external load when the load is equal to the internal resistance of the source. So down here, we show you a mathematical approach to prove that when the resistance of the load is equal to the internal resistance, you get maximum power. And this is derived by using differentiation, by putting dPdr equal to 0. At the A level, the proof of the maximum power theorem is not required. And when the load resistance is equal to the internal resistance, we also need to note that it means that the efficiency will now be just 50%. So the maximum efficiency that we can attain based on the maximum power theorem is 50%, which means 50% of the energy will be lost